but I'm going to go ahead and, so we're going to go ahead and get started. I'm going to go ahead and show you what the data should look like when you take it in. So I'm going to go ahead and share my screen. So here's just the screen. And so what I want to do is I want to go into Excel. And this is somebody's data that they brought into Excel. And what we want is we want the data to be in what we call tidy data form. And what that means is that every single row is a new unit of observation. So I'm not going to talk about what this data actually is, but let's just say that this was, and again, I don't want to know what it is and we're not going to talk, but let's just say this is a certain house's prices. Let's say this is in hundreds of thousands of dollars or something like that. And this was their price now, and this was their price in 2008. So in this case, if we want to compare, if we want paired samples, then this data makes sense to do it this way if we're going to compare the difference between the price now to the price back in 2008. So the question is, if that's your question and it's paired data, then this is the exact right format to have. With paired data, every single row has one unit of observation. Every column is a different variable you measured at different places. If, however, this data is written in the form of, is taken as independent samples, so this 2.469 has nothing to do with this 2.589. These values don't belong together. They're not paired in any fashion to each other. Then this format of the data doesn't help me at all. And what I need to do is I need to actually copy all of this data, because these two columns belong together, copy these, and actually probably cut them, and then paste them at the end of my other rows. And I actually didn't mean to keep this one, so this row shouldn't be there. I'll get rid of that row. So now, each row, the first column is the date, and the second column is the price. So let's say now instead this was the price of, let's say, eggs on a specific date. Then, and these were the price of eggs on a different date in 2008. Then this data makes more sense to have it in this format because these values didn't belong together. They weren't one unit of observation, whereas now they are a unit of observation. The only problem with this is because of these dates, I can't compare with these the way they are. So what I might do is add another column in, which is my factor. Maybe I'll call it date or year. Year might be, or time period, something like that, so time. And then I'd put that this is the present, because I want 2018-19 to be considered the present, or 19-20 to be considered the present. So I might call those all the present, and all the ones that were in the year 2019 or 2020 would be considered present, and then this might be past, or whatever you want to call them. And then I'd have this column for past. And so we're now in the right format to be independent data. Independent data, you have one variable that has all of your values for that one variable, one variable, and then you have another column which is your factor variable. So that's how you kind of want to set these up, is to kind of make sure that they're in the right format. It depends on if you're paired or independent. If you're independent, it needs to have one column with all of your prices in that one column, and then another column with all of your, whatever you want that factor to be. It could be gender, it could be race, it could be whatever it is that that other factor is that you're basing it off of. And if it's paired, then you would have them all in one, they'd be next to each other. So it'd be the original way we had it. So this is independent, would be in this format where all your variables are in one column, and then you have a factor variable. If I went back to where I had it before, if it was a paired sample, again, these would be one unit of observation, and we have two variables that we can subtract with paired. So that's kind of what you want to look at with this, is how your data is. If you need help putting your data in the right format, send me your data, and then I can, and tell me whether it's paired or independent, and I can help get you in the right format. Then make sure, go ahead.
Is it cool if I ask a quick question?
Uh-huh.
So I'm doing housing prices for 2019 or from 2018 compared to 2019. Can I use this one currently you have on your screen, or would it be better to do the one that you were suggesting where it's all one column?
Well, again, it depends on if you're using it as paired or independent. So if you're considering this house price here is the same house as here, so the housing, like my house price is more than it was in 2008, but not because I've changed my house, it's just because the way the market goes. So I would consider if I'm using the same house from 2008 to now, then it would be paired and I'd want to use it in this format.
Okay. Yeah.
So you have to kind of answer that question first.
Copy.
Okay. The other thing is then you want to go into File and do a Save As. And to take it into RStudio, you do need to have it in, you do need to have it as a CSV. So you come down here when you're going to go save it, you're going to put the name in here. And then right below it says Save as Type. And you click on that and you pick CSV. So make sure you've saved it as a CSV, and that way you can work with it. I'm not going to save this, but that's kind of what you want to do. Does this all make sense?
Yeah, so basically if we have like two different types, like for mine, I was doing high population areas and low population. I'd need another variable to designate which is high and which is low.
Yes, so you'd have like a variable of population type and then high, low. You'd use the words high and low. Okay?
Alrighty.
And again, you can send me your data and I can help you put it in the right format if you can't figure it out. All right, so I do want to go on to where we were. I don't want to save this, so we were dealing with talking about chapter 10, which was regression and correlation. I actually reorganized this a little bit and put in headers so you could actually click on this and say, I want to find out more about scatter plots or residuals or different things you want to look at. We were in the midst of doing a hypothesis test. So I want to finish talking about that hypothesis test that we were doing last time. And then we're going to get into a couple more concepts here. So again, my question, and this is where I'm seeing when I'm grading your tests, I only have 3 more people's tests to grade and then they'll all be graded. But what I'm seeing is that you're not getting a really good idea of what the question is. So I want you to really pay attention to the question that's being asked, or for yourself, what question you're actually asking and how do you then use data to answer your question. So my question really was, is there a linear model? That's really my question. My question is there a linear model between height and foot length? That's my question. Because if there is, then I can use that model to tell me what somebody's height is if I know their foot length. And you may say, well, why do you need this kind of stuff? But, and this is gonna be a morbid thing, but let's say you find just somebody's foot, which sounds gross, but let's say you find somebody's foot, you can actually recreate how tall they were based on the length of their foot. And they actually do this in crime studies. They look for that kind of information. So there actually are reasons to do things like this, is to be able to predict this kind of information if you only get that information from something. So not to be morbid, but that's something you could do. So the question is, that's what you want to think about, is that's your question. And your HA is kind of that question. All your HA is the question you were asking. We were asking, is there a linear model? So my HA is, there's a linear model. That's what I'm going to assume. I'm going to assume there's a linear model. And then I'm going to go see if I have evidence to actually prove that. So HA should always be whatever that question is that's being asked. So like on the test, I was asking if the new method for teaching mathematics created higher final exam scores over the old method. So my hypothesis, my alternative hypothesis, my research hypothesis, whatever you want to call it, is the new method produced higher final exam scores over the old method. That's my question. And that's what your HA is. The HO, it doesn't really matter. In fact, there's people out there that argue we shouldn't even worry about null hypothesis anymore. But your HA is really the question you're trying to ask. This is what I want to know. Is there a linear relationship between foot length and height? And your HO is there's not. So that's kind of where we go. I didn't tell you this before, but we usually test at the 5% level, sometimes the 1% level. You're actually answering that question pretty well on the test. So make sure you look at how you answered it on the test. If you didn't answer it right, you should look at my answers so you can see how to do that. But that just tells you how you determine whether something's unusual. That's just, all that number is important is this unusual or not? Again, every single test has your assumptions. And these are the ones that just say, this is a valid test or it's not a valid test. Nothing else. There's no other purpose behind these assumptions. It just says, was I allowed to do the thing I did or was I not allowed? Did I break the law by running this test is kind of a way to think of it is. Your assumptions are, these are the things that must be true in order to actually run this test. And if they're not true, you really couldn't do what we did. Now, these days we have resampling techniques that we use, and I've touched a little bit on those, not much, but a little bit on resampling techniques. And they are ways that we get around the assumptions because they don't have very many assumptions. All of these actually have this first assumption. You really should have a random sample if you can. Isn't it? All right.
Thank you.
So you really should have one if you can. It doesn't always work, but you should. The second assumption, randomization, takes out, you don't have to worry about whether or not you have a normal distribution, but we're still in the more traditional way we're doing things in this. So we do still need that normal distribution. And the way we check it, the way you check in your random sample is you just describe how you took the sample. If the problem tells you it's a random sample, great. In your project, you don't have a problem telling you if it's a random sample. So you would just describe to me, how did you get a random sample of 25 values? And again, if it's paired data, it's 25 kind of total, 25 pairs. And if it's independent data, then you should have 25 and then 25. Okay. So here, the way we check the normal distribution one is we look to see if we have a linear relationship from our scatter plot. Again, it's not perfect, but there does seem to be a linear trend to this. So you could say, yeah, it kind of is. And then we also look at the residuals, and we talked last time about how we create those. We can create them, and again, this is just telling you how different what we measured was from what we predicted, what the model predicts. So the model and what we measured and what we modeled was off by 0.9. The negative means it's below. The model value is, the measured value was below the model. Positive means the measured value is above the model. And then you're looking at numbers is way too much work, so we look at graphs. And again, we're looking to see if there's any kind of pattern to this. And you told me last time it looked kind of random. Okay. There's a little bit of a pattern because we have all these kind of dots here, but not really too much because they're kind of still all over the place. All right, so it's safe to assume that there is a normal distribution for height. So that's where we get into our calculations. And I was a little worried yesterday when R was down. And again, R was down because CenturyLink system went down. It was not the college that had anything happen to them. It was because of our provider went down. But I was a little nervous, so I ended up putting all the data into here. But I do want to show you how we calculate this. So I'm going to show you how to do this, and then I actually already put it into the Google Doc. But I'm going to go into RStudio. So we're going to go into RStudio, sign into it. Again, if I'm not in an RMD file, if you want to create one, all you do is go up to File, say New File, and say R Markdown. That will create an RMD file for you. RMD means R Markdown Document, RMD. So if you want an RMD file, you can go do it this way. If you don't want one and you just want to work in the console, which is what we're going to do today, you can do that too. I just want to walk through one more time, how do we get the data into here? So we're going to go over here to upload. Oh, actually, first we're going to go to packages. And if you create an RMD file, you're going to have to put in the language to put the packages on. So you just have to go into my RMD files and copy the first few lines of it. So all the way down to where it talks about libraries, get all those in there. If you aren't using an RMD file, then you just come down here to packages until you find Mosaic. And as Jacob found out, he went ahead and you can actually download R and RStudio onto your computers, and it works beautifully. It's free. You don't have to pay for it. If you have a Google Doc, I mean a Google Chrome book, you can't, and that's why we went to the server. But if you have a Mac or a PC, you can actually download it onto your computer. But as Jacob found out, Mosaic's not in there. A bunch of other things aren't in there. So you'll need to load a bunch of information in there. What we're gonna do now, because Mosaic isn't here, because we've uploaded those on there for the college, we're gonna just put in Mosaic. We're gonna click on it, make sure it loads. And then we're gonna go into files. I'm gonna upload. So I'm gonna go choose my file. It was somewhere in downloads, and it was class data. Class foot is actually what it's called. So I'm gonna click on class foot. I'm gonna say I wanna open that. And I'm gonna say okay, because it says class foot here. And I'm gonna say yes, because I already did this before. So if you've already done it before, you could also override it. It's up to you. And once you've uploaded your file into here, you'll find it in your list of files. It's right down here, usually at the very bottom, but not always, but usually at the bottom. Click on it and say, I wanna import it. So you wanna import this data set. And then the only thing I would suggest you do, this just shows you kind of what the data set looks like. I would get rid of, I wouldn't change the name up here, but I would get rid of this sheet 1 and just call it class foot, just because this is gonna be the name of the data set. And you don't want the data set or data frame to be really long name. So I just changed it to class foot all by itself. You can import it, and there it is again. So we did this last time. I just was reminding you how to do that, so you can do it for your project also. And then one of the things we also did last time is I created a new variable called lm.out. So I'm going to actually do the same thing again. I want to create this lm.out, and we actually use this a lot. So this is why I keep doing it every time. Make sure you can do this. That little greater than symbol dash is just saying everything that's beyond here, we're going to save into this name. So everything goes after what we just typed goes into this lm.out, and that's going to be lm. And then we are looking at height versus length. So height is my response variable. Length was my explanatory variable. So you always want to put your response variable first, and then your explanatory variable second. Then you do have to tell it where the data is. And it was class foot. And hit enter, and again, it looks like nothing happened. But if you come over here to your global environment, you now see lm.out is a listing in this variable, this listing. So you'll now see this is actually here. It's actually created whatever this is. You can click on it to look at it, but it really isn't much to look at. Okay. And we still haven't actually done anything with finding the hypothesis test calculations. We're about to do that. So we did all this, we can do those. And what we type is in summary, just type the word summary, lm.out. Hit enter, and there it is. So again, we're doing summary, lm.out. You do need to do this lm out first. And if you get a new data set, you need to redo this lm.out because it's going to be for the class data. And even if you change the class data, you're going to need to do this again. So you always want to kind of recreate that. And then you want this summary lm.out. And what it does is just summarizes everything that's in that lm.out. It tells you, and I'm going to move this up just a little bit so we can see a little bit more of this. It tells me it's going to call the formula LM, which is linear model. The formula is height, width, length, and the data is in class foot. So this is just telling you, hey, this is what I used. So make sure that that is what you want to use. It gives you the residuals, but it's not all of them. There were 50 some residuals. This is just kind of the 5-number summary of the residuals. So your min, your max, your quartiles, and your median. So that just gives you an idea of what they look like. You don't want them to be way off base, but there's really not much you want to look at there. The next thing down that tells you when you did this is it tells you the coefficients. It actually tells you this whole table. And so it actually will tell you your coefficients. That's what this number is here, and this number is here. So remember, what's the equation of a line?
Y equals mx plus b.
Y equals mx plus b. So m is your slope. That's the thing that's in front of your x variable. And our x variable in this case was length. So length, there's my length, and this is the coefficient that goes with the length. So that is my slope. The intercept is exactly what you think it is. It's your y-intercept. And so this number right here is my y-intercept. We did this before when we did LM. We did just this part of the statement. We got the same equation. So we didn't need to do that before because it gives us the equation here. So you don't need to keep doing all these different things. This is the one command you need to do for everything. This standard error, don't worry about that. This isn't really something you are going to need to worry about here, but that's what that is. It's just something we have. People that do statistics for big jobs and such, then they need things like this, but really most of you don't. The next thing over, it says t-value, and that is your test statistic, because t-value is test statistic, kind of think of it that way, test value. We aren't testing the intercept. We're not testing if it has an intercept. We're testing if it has a slope. So it is always going to be the t in the intercept, in the length column, row. So you want this t-value in this length. So that is my test statistic right there. And then right next to it, it says PR, which is probability. So there's my probability value. So we just need all that. There's some more stuff on here that we need that we're going to get to in a little bit. We'll talk about what all those things are. But right now, this is all we need. It's that piece I talked about. So we can now copy this and paste it into my Google Doc. Let's see, where's my Google Doc? I already did that. I'm going to paste it again just to show you what happens when I paste it. Then I'll undo that here in a second. The biggest problem when I do that is this table that it created gets really messed up. The coefficients aren't necessarily where they want them to be. It just make sure you kind of pay attention to what the things are. This one doesn't look too bad, but sometimes it gets really messed up. All right, so what we have is, again, I created that LM out. I did the summary of the LM out. I got all this information, and now I know my t-value. So again, my t-value is right here. So my test statistic, and I think I wrote some things down here, what things, different things are. This just gives you some idea. But here's my test statistic. Here's my t-value. That's 6.586. And then my p-value is this 4.2. Remember that E means times 10 to the -8. So my p-value is 4.2 times 10 to the -8. Is that really big or really small? Is it a big probability or a small probability? Very small. So Jacob says very small. So remember, 4.2 times 10 to the -8 means I've moved the decimal point 7 places that way. Well, actually 8 places that way. And it's a really small number. There's 7 zeros and 4. And that's a pretty small number. So what do? Do we reject HO or do we fail to reject HO? Anybody there? Anybody want to give me an idea of if we're going to reject HO or fail to reject HO in this case?
Yeah, your
So
p-value is tiny, so you could be rejecting it.
Yeah, so I'm going to reject HO. That's the same thing the other Jacob said. So both Jacob said reject HO. Since my p-value is less than my alpha. And that's all that alpha is for. That alpha is to tell you, is this value small or not? That's its whole purpose, is to just say, this is a small number or not a small number. And that's obviously a small number. And when you reject HO, then there is enough evidence to show the question you want to ask. Again, my question I was asking is there a relationship? Is there a linear relationship? And I can now say, yeah, I have enough evidence to say there is a linear relationship. So I can actually reject HO and say, yes, there is evidence that there's a linear relationship between foot length and height. So I can now say that. There is a linear relationship. It looks good. Okay. And that's really what you want to do. You want to pose a question. You run this hypothesis test to kind of have the evidence to say it. And then you answer the question, I have enough evidence or I don't. Now, could I have made an error? Yes. Since I rejected HO, I could have made a type 1 error. I have a 5% chance I made an error. But I don't think I did. I think I'm probably pretty good, because I don't think I'm that unlucky that I do things that are only 5% of the time happening. Okay. So I would say I'm doing okay. I probably didn't make an error. And I think I have evidence to say there's a relationship. Right? And that's what we're doing. That's the whole purpose behind hypothesis testing is do we have evidence or no? And if we have evidence, then we have evidence. If we don't have evidence. Now the question is, how good is the model at predicting that variability of the height from a foot length? In other words, people who have the same length foot are not the same height. Okay? We have a lot of people up here. All these people here have the same length foot, but they are not the same height, right? This person's down here. This person's way up here. These people are not the same height. Even these people, they have the same length foot, but they're not the same height. This person's much taller than that person. So there is variability in people's heights based on their foot length. There is some variability. And the question is how good is the model at actually figuring out that variability? That's really the next question we want to ask. And that was actually the purpose behind the group work you did, is how good is the model at predicting the variability of height from foot length? And how do we determine this value? And that group work that you did, which unfortunately I haven't had a chance to grade, but I want you to talk about it, is where we talked about this thing called a coefficient of determination. So does anybody kind of give me an idea of what coefficient of determination was? And the symbol they used was capital R. So does anybody remember from that group work I had you work on what they were considering that coefficient of determination, which is a stupid name, by the way. I didn't name these things. I wouldn't have named it that. But what did they call R? What was R doing for you? Big R. Not little r, but big R. How'd you calculate it? So remember, if you went to that group work, and I'm going to go into it for just a second.
Little r was just big R squared? Or?
Well, it is, but I want to go more of what big R was first. But you're right. It was big R squared. Big R is, if you square it, you get big R squared. And so it really is that. But I want to do a little bit more than that. I want to actually have an understanding of what that is. So I'm going to just go into that group work for just a moment. And talk about that, of what that actually is and what does that do for us. So in that, it had you open this little app. I love when it asks me all these questions. Okay. Okay. All right. So in this, if I was looking, this one was looking at age and income. So what it was saying was that the older you get, the more your income is. All right. And I think it actually had you go into births. And it was looking at mother's age versus father's age. And it was having you do what with this blue line and this black line? What were you doing with this blue line and black line?
Standard deviation and
You know, fucking, you know, motherfucking like, and
the standard deviation was the one on the right, and then the one on the small one, the blue one, was everything that didn't get included.
All right, so yes, you're right. It's the other way around.
It's the one that actually did get included is the blue.
So what this blue line represents here is this represents the standard deviation of the model values. What values the model gives us. And I can actually trace this horizontally so you can see that these were the values that the model gave us. So each of these is from each of the model values here, and I can actually show you the model values. They're tracing over from that. So this is the standard deviation, how much variability there is in the model values. And then the black line was representing what?
I don't know if you know or not, but men are struggling. Men have 4 times the rate
Oh my God,
of suicide, 2 times the rate of alcohol incidents. We
Okay,
have way
who's
more
that?
mental illness in women.
What is that? What was that?
What did you ask again?
I want to know actually what that was that just came over our speakers.
I don't know what that is.
Whose phone is ringing? I'm
I think it might be my.
Okay, so whoever it is, put yourself on mute.
I'm gonna creep up to this stop sign like I'm stalking it.
Okay,
What the heck?
if we can't get this to get under control, I'm going to close out the session. Okay, so whoever's phone and other things are going off all of the time, can you put yourself on mute so that doesn't keep interrupting the class? Okay. I notice a lot of you aren't on mute, and I might mute everybody if it happens again. What does the black line represent?
Oh, let's see.
So you're right about the
model
blue,
value.
not the model values. The blue line is the model values. So what's the black line?
Oh yeah.
Explained.
Standard deviation.
It's the standard deviation, but of the measured values. So this is how much variability there actually is in people's father's age versus mother's age. Actually, the variability in the mother's age for each father's age. So we then looked at this thing called big R, and Jacob said it's the ratio of the blue length to the black length. So again, the blue line is the amount of variability that the model tells you. So that's the amount of variability explained by the model. And the black line is the amount of variability explained just in general, how much variability there is in the data. So when we talk about the coefficient of determination, R is the measure, is the ratio, I should say, ratio of the explained variability. And we're going to actually, because this is actually what R is, not just variability, but standard deviation, over the explained, the total standard deviation. Now, actually, we deal with something called R squared better in statistics. And there's a reason we use this capital R and this R squared, and I'm going to talk a little bit about that. But that is also a ratio, and it's the ratio of explained variability to total variability. All right, I'm muting everybody because somebody is not watching that they're muted or unmuted. If you want to talk, you're going to have to unmute yourself. Okay, sorry. But I keep hearing things in the background and you got to watch yourself, okay? Because again, this is just the same as a classroom. You can't disturb people in class. So this is the same kind of thought. All right, so R squared is that ratio, capital R squared is that ratio of explained variability to total variability. And it actually, because it's really a ratio of that total and explained versus total, we can actually do R squared as a percent. Not R, because R is then taken as square root and things get weird when you take square roots. But it is that ratio and it's a percent. It can be talked as the percent. And that is really what the coefficient of determination is this ratio. And what it measures is how much variability in the Y is explained by the model. Okay. And if it's a fairly big number, then more is explained. And if it's a fairly small number, then less is explained. Okay. So that's kind of how that all works and how that all fits together. And what we need to do is we want to have a way to quantify that. On that group work, you quantified it by looking at that percent. How much is the explained, the blue line percent to the black line. So I'm going to unmute people so you can talk again. I can unmute people. All right. Can't seem to unmute people. For some reason, I can't unmute anybody. That's weird.
I got him muted, but okay.
No, you're
And yeah,
fine. You can unmute
Yeah,
yourselves.
I'm muting myself.
Yeah,
you
that's
have to
fine to
choose
do. So we're gonna wait on other people. But one of the things I want to point out is that you actually looked at this ratio. So in this case now, what percent of the blue line is the length? Is it the length of the black? What does it look like? What percent does it look like? The length of blue to the length of black.
Looks like about 50, a little more.
Yeah.
Maybe a little bit more than 50. Yeah, it's really hard to say that and what it exactly is. And we actually can go into the statistics and actually see what it is. So big R squared is about 0.59. And it is basically, if you take its square root, you get that ratio of about little r, no, big R squared is about 0.35. Big R is about 0.59. About, you said about 50%, a little bit more. So it's about 50%, it's about 50, almost 60%. Little r is also 60%. We're going to talk about this little r here in a little bit. But it's the big R that I care more about. That big R is that ratio here. And if you square it, you'll get what big R squared is. You actually get that coefficient of determination value. And what this means is, in this case, is 35% of the variability in mothers' ages is explained by the model, which in this case just involves fathers' ages. So in other words, that doesn't mean it's perfect. It's not great, but 35% is pretty good. 35%, I can actually basically tell you what a mother's age is going to be based on what if I know the father's age. Not always. Only about 35% of the time can I do that, but it's not too bad. And then again, that's not exactly what it means, but it gives you kind of an idea of what to talk about. So that's what this number actually represents, is that value, that 35% gives you that. How much variability in the mother's age is explained by if I know the father's age. And again, it's not perfect, but usually a woman, man and woman marry each other that are around the same age. Not always, though. My father is 24 years older than his wife. So not always are they around the same age, but a lot of times they are. Okay. We can actually find this out also here. We can find the coefficient of determination for the data we have. And we actually already have it. So if I go back to that summary of LML that we created here already, I actually already have it. It is right here. It's this thing called multiple R squared. So this multiple R squared right here is actually that R squared value I want. And so I can now say my multiple R squared for this is 0.4908. And what that means, the interpretation of that. So I'm going to say for the foot height and foot data, the multiple R squared is this value. So the coefficient of determination is this. The interpretation of this is that 49%, because I can make this into a percent, except I'm going to use percent symbol, 49% of the variability in the height of a person is explained by the model. Okay. And that's all it means. Is 49%, that's not bad. That means with about 49% of the time, I can actually tell you what somebody's height's going to be. Not really. I mean, like I said, it's not exactly what that means, but it just means I have a way of telling you how much variability is. It means that just by giving you, just if you tell me somebody's length of their foot, I can tell you their height, and I can give you with a fairly good amount of, I won't say confidence, because this isn't a confidence interval, but just fairly good answer, okay? The reason we like R squared over this thing called R that all of you seem to love, and I want to get away from this little r, and we're going to talk about what little r here is in a couple minutes, but the reason we like the big R squared, and even the big R, is that, and the reason I use the word model, is this model here that we were looking at here. Whoops, wrong place. Sorry, I hit the wrong place. I don't know how to get back. All right. Is if I go over here to this, if I were to add in a covariate of, let's say, did anybody pick a good covariate they worked with? Anybody get something? Let's go ahead.
To pick our covariate within those two.
No, you can pick something different if you had a different set of variables you worked with.
Okay.
I was going to pick maybe baby's weight as my response and gestation. So that's pretty good, right? We have a pretty good value with that one. That
I actually found that in the group work, the covariate, what you think would increase or decrease, it often isn't what you would expect.
Uh-huh. All right, so which one did you pick? So was it mother's age and father's age again? What was your covariate?
Were you asking?
Jacob, you just said you found a good one.
Okay. Pull up my. Give me a second to pull it up because.
You don't remember? Because that's okay.
No, I just need to pull up the group work if I can find it. I'll let you know when I find it.
Yeah,
Okay.
I've got mine pulled up.
Okay, what did you pick?
For my response, I did BMI. For explanatory, I did sleep hours, and for the covariate, I did depressed.
Okay, so you did BMI,
Mm-hmm.
and then you did sleep hours.
Mm-hmm.
I'm gonna find sleep hours. I'm not finding sleep. I know it's here.
There it is.
Yep.
Underneath first baby age.
Okay, and what was your covariate?
Depressed.
depressed.
It was like near the
Oh, there
top.
it is. Oh, wait, go back up a little bit.
There
Right
it
under.
is. Okay, got it. All right. So in this sense, you're looking at the fact that you've got a covariate in here. And so we have a lot of variability in the data, just what we collected. There were a lot of people who were different in the number of sleep hours they had, and actually their BMI based on their sleep hours. And then you looked at their BMI, their BMI based off of also whether or not they were depressed. And so we can also estimate what the R squared would be based on this. And what R squared did we have here? Does it look like? So,
Very small.
huh?
It's going to be very small.
It's gonna be very, very small. It's gonna look like it's
Oh, I
maybe
can-
20%.
Oh, there it is.
Yeah.
Yeah.
Okay, so if I went and looked at the statistics, it was about 22%. I was pretty good with my 20%. Okay, 22, so 0.22. And my R squared, therefore, is 0.05. It's pretty dang small, which means it's not a very good model. This actually is not really good at telling you what somebody's BMI is based on it. But the most important thing is that that little r you can't do. So if you add any more variables, which is what all covariate is just adding more variables into your model, you can't use this little r thing. And that's where we like to deal with this big R squared and even the big R. All right. So Jacob, did you find yours?
Yeah. Are we just looking for any, or if it makes it larger or smaller?
Let's look at one that makes it larger, maybe.
Yeah. I did response of baby weight, and the explanatory is gestation.
Okay. And what was your covariate in this case?
It was induced.
Induced. Oh, induced. Interesting. So that wasn't very good either.
Wait, no, I got mine as an R of 0.74.
Oh, well, let's try a new sample. There we go. So I just took a new sample. All right, so now looking at this ratio of the blue to the black, it does look like it's about 50% or a little bit more. And then if I go look at my R was about 0.49, so I was about right, about 50%. And again, that little r is invalid. You can't do that. So this is why that little r is not useful and why we like this big R, this coefficient of determination. Okay, so this is what we're dealing with, is this coefficient of determination. And that's kind of what we always want to look at, is the higher this is, the better the model is at being predictable or predicting. The smaller this is, the less good it is. Okay, so that's kind of what this all fits in and why we deal with this coefficient of determination. We want this value to be closer to 100% if we can. It doesn't always happen that way, but it can happen. If you take the square root of that, you get this big R instead of big R squared. But big R squared really is this coefficient of determination. Okay. And then it asks you in the group work to look at the big R and the little r. The little r is actually something called correlation. And a lot of you have used this term correlation throughout this course. And I keep telling you don't know what correlation is. And so now we're going to talk about what is correlation, so you understand why we don't care what it is. And all correlation is how strong the relationship is. That's all it does. It's a measure of how strong the relationship is. The closer you are to 1, the stronger it is. The farther away from, the closer you are to 0, the less strong it is. It doesn't tell you anything more than that. What I'd like to do is draw you some pictures that show you what is, again, a good correlation or what different correlations might be. But again, this coefficient determination is better because if you have these covariates, if you have these extra variables in your model, which you should have, because a lot of times models aren't just one thing. In fact, in here, foot length and height, I could add gender into this. We've already talked about the gender is probably my covariate, and I could put that in. And I could have done that up here, I've created that, and we might actually go do that here in a little bit and see what kind of values we get. But this correlation can't be done unless you only have 2 variables. So it's not just how strong the relationship is, but how strong the linear relationship is between two variables. Whereas the coefficient of determination, and even big R instead of just big R squared, actually works for all, however many variables you may have. But this correlation only is a measure of how strong the linear relationship is between two variables. And that also reminds me, coefficient determination works for even nonlinear models, whereas R only, this little r only works for linear. So the symbol is little r. Okay. So what I'm going to do is I'm actually going to show you some graphs. I'm going to create some graphs that show you kind of what we consider strong correlations. You can know what these different things are. I actually happen to have, we use this whiteboard I have to kind of show you this. And I'm going to draw some pictures. If I can get my, there we go, get my pen out. Okay. And so I'm going to go ahead and draw you some pictures if I can get my pen to work. There it goes. Okay. All right. So we are almost always in the first quadrant that we're dealing with because we're usually dealing with positive X values and positive Y values. Positive explanatory variables and then response variables are usually what we deal with in life. It's very rare that you have negatives. So we almost always draw them here. And what I want to do is draw you a correlation. I'm sorry, draw you a scatter plot between two variables. And so this might be my scatter plot. Okay. But I'm going to draw you a couple more also. So I'm going to draw you another one. Okay. I'm going to draw you one more, and then we're going to talk about each one. All right. So of these three that I've drawn, which one looks like it's got a fairly strong, well, remember, these are all linear relationships. So even though you want to think of these only in terms of linear and nothing else, no quadratic, no exponentials. So of these three graphs, which one looks like it's a fairly strong linear relationship?
The first one?
The first one looks like it's fairly strong. So we actually would call this one a strong correlation. But all that means is these two values are linearly related in a strong way. Doesn't tell you anything else about those. What about this between these two? Which one do you think is better between these two?
The second one.
The second one, yeah. Well, you mean the second one by the second one I drew, right?
Yeah, the middle one.
Yeah, the middle one. This one looks a lot stronger than this one. What about compared to that? Is it as strong as this?
No.
No. So this bottom one looks pretty dang weak. And so we'd actually call this a weak correlation. So if the first one's strong and the last one's weak, what do you suppose we could call the middle one?
Like mid or medium?
Yeah, we actually call it moderate. But close to it. You know, you could call it weak, medium correlation. You could call it any of those words would be fine. The word we usually see is moderate correlation. Okay. I want to draw you a couple more pictures. One more. Actually. Okay. So what do you really think about this one? I'll call it, why don't I give these names? So we'll call the very first one A. Call the next one B. Call the next one C. Call this one D, and the last one F. So what about D? What do you think about its correlation? Strong, moderate, weak?
Yeah, like moderate.
Moderate, maybe? Anybody want to think it's strong? Jacob thinks moderate also. Okay. I might go with strong, by the way. So there's different answers. There's not one answer. This is actually why this is also very subjective, because you might think it's something different than I do. I think this one's actually pretty strong. I see a kind of pretty good relationship going here. It seems like they're all following along on dots. It's okay, but that's fine. Now, how is this D moderate different from this B moderate?
Let's go in the opposite direction.
Yeah, so what do we call this one? What do we say that this one is? If as X is going up, what's Y gonna do?
So would it be moderate positive correlation?
Yeah, so this one is positive. So we would say moderate positive. Okay. So that means this first one we should also say is strong positive. Okay. And then Jacob says that this one is negative. So this is a moderate negative correlation. What about this weak one? Is it positive or negative?
Positive.
It kind of looks positive. So a lot of times it's hard to say with weak ones whether they're positive or negative, but this kind of looks like there's a sort of positive trend going. So we could say this one's weak positive. So when you're describing this, what kind of correlation you have, you should always have a weak and positive or negative, or strong. So you'd have this quantifier of weak or positive or moderate. You should have this quantifier of positive or negative. What about this one?
It's not linear.
Not linear. So this one actually has no correlation. Okay. Because it's not linear, and no correlation is about linear. Whereas big R and coefficient determination isn't just about linear. This correlation is just about linear. Okay. But does this one mean it doesn't have a relationship? Is there a relationship here?
Yeah, because it's still in the same data plot thing.
So what relationship do you think? I mean, remember when I talk about relationship, I want to be able to find out what equation I could fit this to this. So relationships are things like linear, quadratic, exponential, periodic, those kind of things. So what relationship does this one look like it might have? Anybody know what this one's called?
Quadratic?
Yeah, this one looks like it has a quadratic relationship. So there's no correlation here, but it has a quadratic relationship. So one of the things I want to caution you on is something that's said to have no correlation does not mean that there's no relationship. It just means it's not a linear relationship. So no correlation just means no linear relationship. But there could be another type of relationship. Okay. All right. I want to draw you a couple more pictures. I'm going to go to a new page. I'm going to copy these into where we were, but I just want to draw a couple more pictures here. The next one. What do you think about that one?
Well, it's definitely not linear.
Definitely not linear. So we would say there's no correlation here, right? And in this case, is there a relationship? Looks a little bit like a rubber duck, thanks. But actually there's none. I can't sit there and say for a certain X value, this is what the Y value would be. Because my X's are all over the place, my Y's are all over the place. This is actually no better than just using the mean and the mean or the median. So in this case, there's really no relationship whatsoever. There's no correlation. All right, couple more that I want to draw you. What about this one?
Linear.
It's linear. So does it have a correlation? Is it strong, moderate, or weak? Extremely strong. Exactly, Jacob. Exactly. It is what we consider extremely strong. In fact, if I were to draw a line through this, it would hit every single one of these dots. So we actually call this one perfect. So this one is perfect correlation. Okay. Is this one positive or negative?
Positive.
So this one is perfect positive correlation. One more. I bet you can guess what I'm going to draw.
Perfect negative.
Yeah. So this one is perfect negative. So unfortunately, these quantifiers of positive, perfect, and moderate and weak aren't great. We don't have any great idea for them. We want to have some kind of number, and this is where correlation comes into play. So I want to tell you, we actually, as you saw in the group work, there actually are numbers for these correlations. If I go back to my group work, back to this, and actually we'll go back here all together. I have to reload anyway.
I know that was so frustrating because then you'd get a different data set.
I know, it's terrible when that would happen. So, and it doesn't seem like it wants to work. But we can get this thing called little r. And little r turns out to be that value that you can get from there. And little r is a number between -1 and 1. Okay. So those are the values we can get for our little r. Again, I do want to reiterate here that no correlation means no linear relationship and not necessarily no relationship. Because there could be a relationship, it's just not linear. Okay. And I am going to copy these and post them into the group work. I mean, not the group work, into this Google Doc here in a little bit. We're almost out of time, so I probably won't take the time to do that. But I just want to tell you what these quantifying values are for R. Again, R can be a number between -1 and 1. And I'm going to start with the perfects. And I'm going to start with this no correlation. No correlation would have an R approximately equal to 0. I'm saying approximately because it may not be perfect, but it's going to be really close to 0. So this R would be approximately 0. So like 0.02 would be considered this. A perfect positive would have an R exactly equal to 1. And a perfect negative, as Jacob just said, would have an R of exactly equal to -1. Perfect. So that being the case, can we kind of guess what we think these might be? Closer you are to 1, the stronger you are. So do you think the strong one would be, what kind of R value would we have? And this is little r. So what does it look like this might be? And this is guessing, by the way. There are no right answers here. So moderate's probably around 0.5. So let's go with this strong. What then would you get for strong, do you suppose?
So like 80%?
Yeah, well, I mean, these are percentages. So these are actually just decimal points. So it'd be 0.8.
Okay.
And this moderate might be close to 50%. So R is approximately 0.5. And again, these are just approximates. You could have set 0.47 for all I care. Something close to that. This moderate weak, anybody want to give a value? Moderate weak, probably around 0.2. Yeah, probably about 0.2 would be good. Okay. This negative moderate would be then for what? Jacob says about negative 0.5, and that's right. So remember, because it's negative, your R better come out as a negative number. So don't forget to put that negative sign on it. This one here would have what kind of R?
0?
Yeah, this would be really close to 0. And again, it may not be perfectly 0, but really close to 0. But again, an R close to 0 doesn't mean no relationship. It just means no linear relationship. It could mean something totally different. Okay? So this is what correlation is. We actually can find it quite nicely from what we have. So we actually have the R squared value here. The R squared value is, we came up with was 0.49008. Our correlation value is just the square root of that. And you saw that, right? You saw that your little r was approximately what the big R was, which is the square root of whatever R squared is. So your little r value, your correlation value, equals the square root of your big R squared. Okay? And if you want to, our studio can do this for you. This is not why this is called our studio, by the way, because of correlation and such. It's just called our studio. But if I want to, I could find the square root. Remember, SQRT is square root. So I want to do square root, and then in parentheses, just say what number I want to find the square root of. And I want to find the square root of my multiple R squared. So this 0.4908, I can actually copy that, paste it right inside here, hit enter, and it'll tell me what that square root is. So it's about 0.7. So our value, if we did this and calculated what our R squared, our little R value is, our little R value in this case is that number right there. So 0.7, so can you interpret that? What would the interpretation of that be?
70%.
Well, remember, they're not percentages. So unfortunately, big R squared is percentages, but the little r and the big R are not percentages. These are just numbers. But we can talk strong, moderate, weak, positive, negative.
Strong.
Strong, it looks like it's probably strong. I would call this one strong. So strong correlation. Now we have to figure out, is it positive or negative? And unfortunately, when you take a square root of a number, you have to put that plus or minus sign on it. So the way you determine if it's positive or negative is you look at your slope. Was our slope positive or negative? Way back here, we did our slope. Well, actually, it was here. When we found our slope, remember our slope was right here. Is that number positive or negative?
Positive.
Positive. So that means our correlation is positive. All right, and that's it for finding correlation. That's all you do to find correlation. Notice they don't, R doesn't care about finding correlation itself, so it does it this way. There is a way to make it do it. I think it's something like core of your variables or your linear model, something like that, but it's just easier to just take the square root of your R squared. Then you just have to put the sign on it and just say it is positive since the slope is positive. So what I want to just mention, I know we're out of time. So I just want to mention that on Monday, we will be finishing up chapter 10. The homework for chapter 10 is due the Monday of finals week, the week after. On Monday, we'll finish up chapter 10. On Wednesday of next week, we will be doing a group work over all of chapter 10 material and kind of another review for the final. So it really isn't a group work. We'll work through it together as a group. And we'll kind of talk about how we're going to do this and what the final is going to look like. I am then going to hand out the final after class. And then the final will be due the following Wednesday. So you'll get a week to work on the final. But next Wednesday will be kind of a review for the final. But Monday we finish all of chapter 10. Okay? Everybody good?
Yep.
All right. I will see everybody on Monday. You all have a good weekend. Let me know if you need any help. I do need to stop sharing and say goodbye to everybody. So let me know if you